Hi class, let me give you some hints on assignment number 7. Okay, so the primary focus is on finding limits, okay, based on basically the region and also based on the type of coordinate system we use to evaluate the integrals. First question is basically a question on application of a double integral. Wants to find the center of mass and moment inertia of this region R, okay, about the x-axis. So you need to basically know the formula for center of mass, x bar equal to 1 over mass, okay, double integral over that region R, then and then x times delta xy and dx and dy, and y bar is fairly similar except that this is y at here, right? Okay, so the mass, right, also require a double integral. Mass, okay, equal to the double integral, just the density, and dx dy. Okay, so how do we find the limits for the double integral? So you evaluate this double integral and that double integral, and then you find the center of mass. So for this double integral here, we basically first we need to decide on the order of integration. So in this particular case, you're going to have to evaluate using dx first and then dy, because if you look at the boundaries here, this is x equal to y squared and this is x equal to y minus y squared. So there's no way you can find an expression in terms of the y for the y in terms of x for these bounds here. So that's why we decide on the dx first and dy. So if you dx first, we draw a line in x-axis direction. First contact is x mean, second contact is x max. X mean is y squared, and x max 2y minus y squared. Okay, and delta xy is y plus 1. Right, so that's inner integral. Then the y is sweeping this line across the whole region R from 0, and here you will find that the intersection is 1, so 0 to 1. Okay, so this layout of double integral of this one here will be the same as this, so there's no difference. And in terms of moment inertia, the formula, this is moment inertia with respect to x-axis, so it's y squared delta xy density and dx dy. So same integral region, same limits. Okay, just the integrand is slightly different. Okay, so you can try evaluate that integrations carefully. Okay. The second one is a triple integral, and this is triple integral in Cartesian coordinates. Okay, calculate the volume, basically the region D. Okay, and region D is sandwiched by surface y equal to x squared and the top plane y plus z equal to 1 and the bottom xy plane. Okay, so on the side here, okay, so the bottom, this curve here, and that's y equal to x squared. Then if you extend it up, okay, so you get the side surface. It's like a cylinder, kind of straight surface here, right? And intersecting the top plane. Okay, the top plane is a plane basically extend this line y plus z equal to 1. Extend this line to either direction, then you get the plane, right? So that's how this thing is decided. If we decided to do the dz first, as we learned, we need to know what the shadow or the projection of the region in xy plane look like. So project this region D into xy plane, we end up with basically this shape right here, right? If you draw it out, the shape of this projection, this is x, this is y, and that's the projection, okay? And this curve is y equal to x squared, and this is 1 here. So once you know this now, then we can follow the steps of finding limit. So what do we do? Starting from the origin, okay, okay, draw a line okay, and across this region D. So first contact is if you z mean, second contact if you z max. So this is in the positive z-axis direction. All right. So then the limits 0 to the top surface, which is 1 minus y. Okay. And then dy. For dy, what you do is you draw within this shadow, right? You draw arrow lines in the positive y-axis direction. First contact y mean, second contact y max. So y mean x squared 1. Sweep these arrow lines across the whole shadow. Then you got basically the x mean x max negative 1 to 1. Alright, so that's the part A. Part B, switch the order of integration here. Then the idea is you need to be able to sketch the shadow. For example, the first one here, if we decided to integrate with respect to y first, then we have to sketch the shadow within xz plane. Okay, xz plane. So what does the shadow look like for part 1 here? Okay. First for the intersection, this curve, right, satisfy both equation, satisfy y equal to x squared and y plus z equal to 1, right, because this is the intersection between the surface and top plane. Then if I substitute y equal to x squared into this one here, we get x squared plus z equal to 1, and that's exactly the projection of this curve in the xz plane, and which is this curve here. Okay, this curve. Okay, so this curve right here is x squared plus z equal to 1. Okay, so in other words, if we draw that curve within xz plane, this is xz, so this is that curve here. Okay, yeah. Okay, so once we have this, now, and then according to the steps, so starting from the shadow, you draw the arrow lines, okay, in the positive y direction. First contact is y mean, second contact is y max. Y mean is on the surface, y equal to x squared. Y max is on the top plane, y plus z equal to 1. So y mean is x squared to 1 minus z. Okay, then dz, dx are based on this shadow right here. So for dz, we draw a line in the positive z-axis direction, and z basically 0 to what? 1 minus x squared. And then sweep this one across the whole shadow, so negative 1 to 1. So that's the layout for this part 1 here. Okay, yeah. So let's look at this one, part 3. If we decided to do the x direction first, then dy dz. So first step, okay, is the projection of this plane, okay, of this region in the yz plane, okay, in the yz plane. So what does that in the yz plane look like? And so let's sketch across this one here. So the projection of this region in the zy plane is actually a straight line. Okay, basically the top of this portion is a straight line here, or the projection is basically this triangle there. Okay, and that straight line is essentially y plus z equal to 1. Okay, so the projection in yz, okay, is this one here. This is the shadow, okay, in the yz plane, and the line is y plus z equal to 1. Then in terms of the finding the limits, first you draw a line, right? First you draw a line in the positive x-axis direction. Okay, so first contact, second contact. Okay, first contact, second contact. So on the other side, it intersects to a negative side of this surface and a positive side of the surface, and that surface is y equal to x squared. So on that side here, we're intersecting. So this is triple integral layout, dx dy and dz. So dx first. So x mean is negative root y, and y x max is positive root y. So this is x equal to positive negative root y, right? Yeah. Then y limits is you draw in the y direction at here for y limits 0 to 1 minus z. X sweep this 0 to 1. Okay, so that's this one here. So the skill of finding the intersection, finding a proper projection into certain planes, okay, is very important. Problem number 3. There are intersection. We're looking for an intersection, the volume intersection between two cylinders, this cylinder and this cylinder. But the drawing at here only shows you a quarter of this, actually 1/8 of the intersection. Okay, and essentially you can try to extend the two cylinders. You know, basically, if you finish all this, or in all directions, right, you'll get the other 7 portions of the intersection. So now we decided to use Cartesian coordinates. Let's say we're going to integrate using this order. Okay, yeah. So for this portion only, first find the projection in the xy plane, and that's this one here. And then within this region, okay, this projection, we draw arrow lines in the positive z-axis. First contact is here, second contact there. In other words, first contact 0, second contact falls into the surface of this cylinder, which is z here, z equal to positive negative 1 minus x squared. Apparently here is positive, so root 1 minus x squared. So that's dz. Then dy dx. So y, this is the shadow right here. So draw arrow lines in the y direction. First is 0, second is this portion of the circle here, and that's this circle. So y minus x squared root positive. Okay, sweep these arrow lines across this shadow, and that's 0 to 1 for x mean and x max. Okay, so then times 8, then you should get the volume of this an object here. Question number 4, okay, is trying to figure out a certain region D such that this triple integral is maximized. Okay, yeah. I'll use a single variable function to illustrate the idea here. So if you have a single function, let's see the function maybe looks like this. All right, yeah. So apparently, if you're going to integrate within this region A to B, apparently what happens is between A to B for this portion, that function f of x, right? For this portion, the function is less than 0, and then for this portion is greater than 0. So the integral, right? We know that single variable, the physical meaning basically is the area underneath the curve. So then, if this is less than 0, then what it means is you're going to have using this area minus this area here, right? Yeah. So that, you know, you can guarantee you get a maximum value. But if we integrate, right? If the a and b is not from here to here, if a and b is from here to here, okay? If this is a to b, then what happens is between this region, f of x is always greater than 0. So apparently, if you integrate it from here to here, you're going to get a bigger value than integrations from it here to here, right? So the idea is like this one here. We want to find a certain region D such that basically this integrand is always greater than 0. Okay, so that's the thing here. So looking for a region D, okay, so such that this function f of xy, is greater than 0. Okay, if that's the case, then we're maximizing this integral here. Okay. this function greater than 0 meaning what? 1 minus x squared minus y squared minus z squared greater than 0. Okay, so this greater than 0 is equivalent to say move this whole chunk to the right side. We get this guy less than 1. So in other words, for any x, y, z, okay, so for any x, y, z belong to this equation here, we got this function greater than 0. And this happened to be basically the interior of a sphere here. So that's essentially the region D you're looking for. So if we're given a region D, okay, within this unit sphere here, so for any point within this region D, you are guaranteed that this integrand f of x, y, z, which is this one, is greater than 0, and that triple integral, right, will be maximized. Okay, so this is basically your region D. Okay, so this one here, triple integral, pretty straightforward. Okay, but I just guess for part A, you're looking at is okay, 4 vertices. The origin here, is 2. This is 2. So connect them up. Okay, so you get this tetrahedron. So I guess the point here is you're gonna have to figure out what is the plane equation for this portion. Okay, yeah. So for the plane equation, you can use coordinate here, then construct 2 vectors, do a cross product, which is going to be the normal vector for the plane. Then use any point here to construct plane equation. So the other way is, you know that at the bottom here, this line is x plus y equal to 2. And the bottom line here, this one is the intersection between this plane and xy here. And here's y plus z equal to 2. And here's x plus z equal to 2. Okay? So apparently, the top plane here is x plus y plus z equal to 2. Okay? So you can test, if you set z equal to 2, you get this. If you set y equal to 2, you get this one here, right? That's how you get the intersection. Okay, so use typical Cartesian coordinates steps, to find the integral limits and then do the integral. This one here is a little bit tricky, but you just need to basically change the typical cylinder coordinates here, right? Okay, so D is the cylinder here, so if I draw the region D, what does it look like? So this is typically what we use for Cartesian coordinates. So if I draw the region D here, region D is the cylinder y squared, so y squared plus z squared less than 9. So y squared plus z squared less than 9, that's the cylinder here. Okay, then if you extend that cylinder, right, then in the x direction you get the cylinder. But x exists only between 1 and 9, so I guess it's only a portion of the cylinder here. So if we draw this, let's draw it again here. So this is x equal to 1, so you have a circle right here. This is equal to 9, for example. You have another circle. Then between here, then you get the cylinder like this, right? So what's strange is, essentially, typically we define our cylindrical coordinates in this kind of a fashion. This is x, y, and then you have this cylinder, and then you define your cylindrical coordinates r, theta, z, right? And x equal to r cos theta, y equal to r sine theta, like that. Okay, so for this particular case, if I just change the perspective a little bit here. So let's say this is my y here, and this is a z here. Okay, then this is going to be the x. Okay, so then what happens is the cylinder is going to be, for this object region D, is going to be like this now. Okay, so here is x equal to 1, and here is x equal to 9, right? And the circle here is y squared plus z squared equal to 9 here. Okay, equal to 9. So now you see, even though our traditionally is x, y, z, but in this particular case, this y is basically this x, and this z is this y here. So in other words, the cylindrical coordinates for this one is y equal to r cosine theta, and z equal to r sine theta, and the z as an x equal to x, right? So that's the set of so r theta x is the cylindrical coordinates here, right? So when you lay out this integral here, we're looking for we're integrating basically the delta function, okay, a certain delta function. Where is the delta function? Delta function is this delta function. Substitute the y with r cosine theta. Substitute z with r sine theta. Okay, so you will end up with certain r and theta function for the y. Then in terms of the integral, we do dx first, r dr, and d theta. Yeah, typically when in this case here we do dz, right? But this is now this side is x. Okay, so x here. So what do we do? First, we need to find the shadow of this object, okay, within yz plane, and that shadow is, of course, it's a circle, right? So within the shadow, you draw arrow lines, first contact, second contact, that's x min, x max, which is 1 to 9. For r, you draw an arrow lines across the shadow, first contact, second contact, so 0 to 3. Theta, sweep that across the whole shadow, 0 to 2 pi. Okay, so now plugging on that, you can do the calculations, alright, the integrals, do it carefully. Okay, so the last one here, cylindrical coordinate to evaluate to find the volume between two cylinders. One is inner cylinder here, and the other top plane is z equal to 3 minus y, and also the bottom xy plane. Okay, find the volume of that. So finding volume is this, but we're using cylindrical coordinate to evaluate the volume. Okay, then dv becomes r dr d theta. So we're going to evaluate with respect to the z first, then r dr d theta. Okay. Yeah. Okay. So okay. So if this is the order right here, what we need to do is we need to sketch the shadow of this object in xy plane. So the shadow of this is basically what does the shadow look like? And the shadow is if I draw it here. Okay. So you have this inner small circle, then you have this bigger outer circle here. Okay. So the inner small circle is a bit too small. So let's draw that a bit of a little bigger here. Okay. Then the outer ones like here. The inner circle is this one. So the center is at x equal to 0.5, y equal to 0. So this is the center with the radius of 0.5. So the radius is 0.5 here. So this side here is 1. And second circle is x plus 1 squared plus y squared equal 1. So the center is at x equal to 1, y equal to 0. So the center is here. And with the radius 1, so this is 2 and here. Alright? Yeah. So that's the shadow of this object in xy plane. Then when we finding the limits here, z first. So within this shadow, okay, draw an arrow lines, okay, across this shadow, across this region. First contact give you z min, second contact, okay, give you z max. So in the positive z-axis direction, z min is 0, z max is on this top plane, which is 3 minus y. Now, but we don't use y, right? Because we're using cylindrical coordinates. So we need to substitute y with r sine theta. So the r sine theta at here. Okay. Now R limits is the trick one. So finding R limits basically means we're going to draw an arrow line. We're going to draw reading lines. Okay, starting from origin here. Okay, across this shadow. So in other words, if I looking at here, starting from origin, this is x, this is y. Draw the one across this shadow here. So this is a shadow, right? Yeah. Then the first contact give you R mean, second contact give you R max. Okay. So let's say this is A point, this is B point. So basically, the OA give you this R mean, and this ROB, right, give you this R max. Okay. Yeah. Now, this is actually where you did a similar exercise in terms of the in the double integral. Basically, let me redraw this here. Okay. So basically, we need to find the relationship between R mean or R max in terms of theta. And theta is the angle from x-axis to where the line is drawn here. So this theta. Now guess what? If I connect this and here, okay, so I have two basically right triangles. One is this and the other is this. Okay, and the hypotenuse here is 1 and the other side is this is 2 here. So what does that mean? That means cosine theta, right, equal R mean, this is R mean, or OA over 1, right, over 1. So R mean equal to cosine theta. And the other one, cosine theta equal to OB divided by 2, or R max, right, divided by 2. So R max equal to 2 cosine theta. So the limit is cosine theta to 2 cosine theta. Okay, so that's the R mean, R max. And the last step is to sweep this arrow line or the reading lines across the whole shadow. Find the boundary, the theta mean, theta max to corresponding to the boundary. So one boundary is here, one boundary is here, right? Yeah. So there are two bounds here, one is here, here. For this bound, this is pi over 2. For this one here, it's negative pi over 2. So the theta limits, right, is negative pi over 2 to pi over 2. Now that's the limit basically for the z, r, and theta. The question also gives you some hints in terms of the R limit set here. As a matter of fact, okay, this R mean equal to cosine theta, or this R max equal to 2 cosine theta, is basically the polar expression for this circle and the polar expression for this circle here. So what happens is, if you substitute x equal to r cosine theta here, or y equal to r sine theta over here, you will get r equal to cosine theta by some simplifications. Similarly for this one here, right? Yeah, that's what today we learned. We said in class basically, you know, this is the expression for the circle using the xy coordinate. If we use polar coordinates, we're gonna get r equal to 2 cosine theta. That expresses the same circle, right? Yeah. Or in other words, you know, basically, if this is a cylinder for this, then r equal to 2 cosine theta describes the same cylinder, right? Yeah. Maybe I'll just so this is r cosine theta minus 1 squared plus r sine theta squared equal to 1, right? That's that's to use this one example. So expand this portion here, r squared cosine theta squared minus 2r cosine theta plus 1 plus r sine theta squared equal to 1. So this one is cancelled, and then this and this has a common factor, r squared. When you take the r squared out, cosine theta squared plus sine squared is 1, so minus 2r cosine theta equal to 0. Okay, so take out the common factor r, so r minus 2 cosine theta equal to 0. So either r is 0 or either r is this, but r cannot be 0. So basically, the only possible solution is r equal to 2 cosine theta. Okay, for this integral here, there's not much of a trick, but you might end up with something you need to use a hint. So calculate something, then if you calculate carefully, you should end up with an integral like this. Okay, so you should have an integral like this. Okay, so from here, this cosine theta square, use the hint. Okay. Okay, and then you should carry on from here, no problem at all. And this one here, that requires a simple substitution rule. In general, what you need to do is probably what you learned is you let cosine theta equal to u, or u equal to cosine theta. Okay, let u equal cosine theta, and then du equal to negative sine theta d theta, right? Yeah. But you know, I probably demonstrated. So what I generally do for this one here, okay, is this. So 7 over 3, so pi over 2, negative pi over 2. So cosine theta cube, okay, I'm going to leave it as it is. Now this sine theta d theta, I'll do this. So this is a d, okay, cosine theta. So what happens is a d cosine theta, okay, equal to negative sine theta d theta. So so you have the sine theta, that sine theta, but there's a negative sign here, so we have to get rid of negative sign here. So we basically put another negative here. So this negative will cancel this negative, and of course this negative and that negative will cancel each other, become positive, right? Yeah. Okay. So then you have this cosine theta, same thing. So then you can integrate. This is basically 1/4 cosine theta to the power 4, right? And then from substitute these integral limits, okay? Then you can calculate. Okay, yeah. So same idea as your substitution rule here, right? Yeah. Anyhow, this is basically the hints I think I wanted to give you for this assignments. Okay, so let me know if you have any other questions.